Hello friends, welcome to the channel Physics for You. And in this channel from last few videos we are doing some experiments, right? So we can say the experimental or the practical series has been started. So in last video we have seen some experiment that is for the characteristics of solar cell, and in this video we will talk about how to find the Young's modulus of a bar or a wooden bar. It is and if that wooden bar is fixed at one end and other end is free to oscillate in the air, then that is also known as cantilever, right? Let me explain you. Now let us consider this is an wooden bar, and if I fix this wooden bar at one point, now let us consider I am fixing here and this end is free to oscillate. So such a thing is called as cantilever, right? So we will find now this is just an example of the glass scale, but when we are doing the experiment, we will find the Young's modulus of that wooden material of cantilever, right? So basically here first of all we will see what the journal talks about and how the methodology to find the Young's modulus. Final target is what we have to find the Young's modulus, right? And yes, you have seen on the chart or on the journal the formula 16 pi square L cube divided by B D cube into M1 minus M2 divided by T1 square minus T2 square. So what all these things we will see here. Basically L means the length of the projecting bar or length of that cantilever, right, from where we have fixed. Now let us consider I am fixing here, so whatever may be the length of this portion, free portion which is free to oscillate, that is what capital L. Breadth means, now see, if I am using this is the bar, then yes, breadth, yes, we know that it's a thickness, the width, we can say breadth we have to find. And D is the thickness of bar. Thickness of bar means, yes, what is the thickness of this bar, that we have to find. So that is denoted by small d. Now T1 is the period with the mass M1 attached to the bar. Now let us consider we have attached two different masses M1 and M2, but here we are not talking about only two masses. We will take several readings near about 6 masses, and from that we will find the slope. So don't worry about this bracket, this completely going to be a slope of that graph. So but for a while we can consider the whatever may be the time required to oscillate, or the time period when the mass M1 is attached, that is what T1, and whatever may be the time period when the mass is attached and that bar is set to oscillate, then whatever may be the time period, that is T2. So those are what the corresponding masses and corresponding time periods. And yes, we know this is Y is what Young's modulus, that's what we have to find. So if this procedure has to be followed, so this procedure I am going to explain very briefly when we are going to the experimental part. Don't worry about this. Simply we have to attach a bar and we have to just oscillate it, and we have to count the 30 oscillations. Now here see how is the observation table. In observation table, first we have serial number, then length of the projecting bar, that is going to be constant. We are going to keep it constant, and we are going to change this mass. Okay, so we will find for different masses, that means for 50 gram, 100 gram, 150 and so on. Let us see. And then time for 30 oscillations. So we will count the time required for the 30 oscillations. Now we have to measure the oscillations. We know that how to measure, as like the simple pendulum. Now I am talking about this. If I am talking about if this pen is set to oscillate from this point, then that will be 0. Then if it goes to the extreme position, that is not again 1, and if it comes to the original position, that will be the 1. So 0 if it went to the other extreme position and comes to the original position, that is 1. Similarly then 2 and so on. Likewise we have to measure the 30 oscillations, and yes, we have to take the 3 trials for a particular mass. Now let us consider I am attaching here 50 gram. For 50 gram I will take 3 trials, T1, T2, T3. Trials are only for the accuracy purpose. Okay, then finally we will take the mean of that, then mean time required for 30 oscillation. But we know that here in the formula we have capital T, so that is time period, and this small t are not same. Time period means time required for 1 oscillation, and this mean time is what time required for 30 oscillations. So we should divide that time by 30, so that we will get the time required for one oscillation, and thus we can call it as time period. Now this is what time period column, and lastly we will make one more column, that is it's a square, time period square. Why it's a square? Because in this formula we have square, so therefore we will make the last column which is going to be the time period square, right. So similarly here we will take for 50, 100 and 150, then 200, 250 and 300. Likewise we will take several readings and corresponding time periods and corresponding time period squares. Okay, now to get this bracketed value, because this 16 is constant, pi value we know, L, yes, you can measure, right. Then breadth you can measure, D we can measure, time period T1, T2 we can measure, right. So these all are what we can say constant, but this is going to be changed with respect to the mass. As mass changes, time period is also going to be changed. As mass changes, time period will be something different. So this is what we can say the variable thing. Almost all things are constant. So to have more accuracy, we are not going to consider only two masses, we will consider more masses, that's what I said, and therefore we will draw a graph, and the slope of that graph will be given by this particular thing, and that will be the more accurate. So finally, as we know that we have these two columns, that means mass versus t square. So we will draw the graph between this mass and t square. So finally, yes, this will be the nature of graph. I am taking t square on x axis and this m on y axis. We can take in reverse manner also, no worries. So if we plot the graph between them, we will find a straight line curve, we know, because since mass increases, time period is also increases linearly. And if we take the slope of this, so we know that this is going to be a slope. Yes or no? Slope, we know, y2 minus y1 divided by x2 minus x1. So on y axis we have m, so we can write m1 minus m2 and t1 square minus t2 square, because on x axis we have t square. So we know this is what we required in the formula also. So finally, if we take this value and if we substitute in the formula, now this complete second what we can say second term, this will be the directly come from the slope of graph. And yes, all the things we will calculate, observations, and finally if we substitute the things here, we will get the Young's modulus, and we know that it is in dynes per centimeter square, because we know it is a force constant. Basically Young's modulus is a force constant, which is force per unit area. So force is measured in dyne, because we are measuring all the things, because the bar whatever we are taking, it is of length in centimeters, its breadth is also in centimeter, width is also in centimeter. So these all things are in CGS units. That's why the unit for this force constant, that is Young's modulus, is also be dyne per centimeter square. If we are converting it into the MKS, then it will be the Newton per meter square. Okay, so this is what friends, the basic methodology to find the Young's modulus. Now let's move towards the experimental part. Okay, so after taking the experimental readings, then again we will come to the calculation part, right. Now come to the experimental part of this practical. So as we told that the cantilever is a beam which is made up of some other material also, but here we have a beam of wooden material, and one end should be fixed and other end should be free to oscillate. This is what the structure, and this is known as cantilever, right. So as you can see, we have attached here on a hanger to attach the different masses, but this hanger itself has a weight, and its weight is 50 gram. Right. So initially what we can say, we have attached the 50 gram weight to the other end of cantilever, and yes, due to this weight you can see now I am taking it to the exact horizontal position, and as soon as I remove my hand, what happens, it starts oscillating. Right. Now that is what we call the oscillation, and we have to count these oscillations, and yes, what we have to count, we have to count the time required for 30 oscillations. We have to measure 30 oscillation. Now see, as soon as I remove, so what I can say, I will say it as 0. So 0, 1, 2, 3, 4, 5, 6, 7 and likewise. But yes, at the same time we have to start our stopwatch, right. That means we have to keep this stopwatch initially, now it is at 0, right. As soon as I remove this and yes, at that time I should start the stopwatch, so that it will count the time also. So likewise we have to maintain, or we have to measure the time required for 30 oscillation. This beam is already measured, or we can say this beam is already printed with the scale, moreover our meter scale. So I can say this is what, from here it is 0 and here it is 70. That means whatever may be the projected part of the cantilever in here, it is how much, 70 centimeter. And you remember that in the chart discussion or in the journal discussion, we have seen that this length is finally we want to calculate the Young's modulus, and it is what, capital L. So capital L, how much, 70 centimeter, right. Next, if you remember in the formula we have small b, that is what, the breadth, right. So this is what vernier caliper. I hope you have seen in the first year only. So this vernier caliper, we can use this for calculating the breadth of this particular cantilever. So how to find? Yes, you have to fix here vernier caliper to this particular scale and then remove. And yes, we have a main scale on the vernier caliper as well as a vernier scale, right. And we know that how to find its least count, minimum division on main scale divided by total number of divisions on the vernier scale. So we have here minimum division, it is 0.1, and total divisions are 10. So 0.1 divided by 10, that means 0.01 centimeter. This is what the least count of this vernier caliper. What is least count actually? Least count means minimum measurement that can be done by that particular instrument. So by this instrument we can measure as possible as minimum up to 0.01 centimeter, right. We know by our normal scale, which is in our box, compass box, we can measure only 0.1 centimeter, that is 1 millimeter. That is what we can say the least count of that scale, right. Now yes, so what I have to do, or what we have to do for to find the breadth, simply put this particular vernier caliper exactly like this, and now we can remove, take the main scale reading, then vernier scale reading, and yes, multiply that vernier scale reading with the least count, add them into the main scale, and whatever may be that is what the breadth, total reading will be the breadth. But we know for the accuracy purpose, maybe this beam is having some irregular shape, finite irregular shape somewhere. So that's why I will take one reading here, I will take another reading here, I will take another reading here. That means what, in the mean of these three readings, the accurate breadth we will get. Okay. So we have seen, or we will see that in the calculation part, how did we find the breadth of this bar or breadth of this cantilever. So one thing is clear, you should keep in mind, this is a wooden bar, wooden cantilever. So whatever we are calculating, that is what the Young's modulus of the material of cantilever. So what is the material of cantilever? It is wooden material, right. Now, so this vernier caliper helps us to find the breadth of such things. So I will keep aside. Let us see how to find, or now we have to find the depth. So this is what we have, a screw gauge in my hand or in my. So this is what we can say, a screw gauge. So by using this screw gauge, we can find even smaller measurements than the vernier caliper. So we know the least count of vernier caliper is 0.01. That means up to that only we can measure minimum. So this screw gauge, we can measure more smaller numbers, more smaller measurements we can do with the help of screw gauge, and therefore we have to use to measure the depth or thickness of this bar. This screw gauge we have to use for that purpose. So again we have to first of all fix this screw gauge to the bar, or if you want I can fix from this side so that you will see. So these are the observations we required for the final calculation, and then finally we will take the reading. So okay, then remove this screw gauge. So I have fixed. Now you can see this is what actually the thickness of that particular bar, and again here also we have a main scale and a circular scale. On vernier caliper we have vernier scale, but here this scale is a circular scale. Now see, I am rotating this, that means this scale is varying. So again we have to take the main scale reading, then circular scale reading, and yes, we have to multiply that circular scale reading with the least count. So for that purpose we must know first of all the least count of this screw gauge. So the least count of this screw gauge is, again the formula is same, minimum division on main scale divided by total number of divisions on, now it is circular scale. So on the circular scale we have 50 divisions, means total number of divisions 50, and on the main scale we have the least value of one particular division, it is 0.05. So 0.05 divided by 50 and it is 0.001 centimeter. Now what was the least count for vernier caliper? It was 0.01 centimeter. Which is the smaller one? Again obviously 0.001 is smaller. That means you can imagine such a small measurement you can do by using this particular screw gauge. So again, to maintain the accuracy, we will take the three different readings, one side at this point, one side this point, and one side this point, and we will take the average of these three readings. That will be the average depth or thickness of this cantilever. So we know in the formula we required B as well as D, and the length also. Length already we know it is 70 centimeter, breadth something we will get, we will see in the calculation part, and similarly depth also. So what purpose we are using these two tools, one is vernier caliper and another is screw gauge. If you want, you can find the breadth also using screw gauge only. Yes, this screw gauge can be can open up to several centimeters. So you can have this bars depth, or what we can say breadth also we can find by using screw gauge, and again similarly we can find depth also by using this. But yes, for more, if least count is smaller and smaller, we know that the accuracy will be more. So therefore what we can say, we will use these two tools for two different purposes. One is for the breadth and another is for the depth. Okay, right. Now let us go towards the reading. So how to take reading? Now I have fixed this bar, one end of the cantilever or one end of the beam to the fixed to this particular table, and other end is free to oscillate. Okay, and such a structure we know it is known as cantilever. So let us start. What I am saying, already the 50 gram mass is attached to this particular cantilever, and that's why you can see it is not exactly in horizontal position, little bit tilted towards the downward. That's why, or why it is, because 50 gram weight is attached. So with respect to this wooden bar, 50 gram is also sufficient, so that it is little bit bended towards the earth or little bit bended towards the ground. Okay, now let us take it to the exactly horizontal purpose, or exactly at the horizontal position. Now I should start this stopwatch, and I should what we can say, remove this bar simultaneously. That is what the task we should do. Okay, and at the same time we have to count the oscillation also, right? So let us see, one reading we will take 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 and 30. Right. So whatever may be the time required, this is what the time required for 30 oscillations. And how much it is? Yes, it has not completed the complete circle, only 5 seconds, 10 seconds, 15, and then 15, 16, 17, or exactly, if yes, it is 18 second. 18 second. That means what? When we have attached the 50 gram mass, now we can reset it. Okay, so when we have the attached 50 gram mass, so time required for 30 oscillation is 18 second, and we know that we are not happy with only one trial, we will take the 3 trials. So likewise for the 50 gram only we have to take the 3 trials, so that if little bit fault is there or little bit inaccuracy is there, it will be maintained when we take the average of these 3 trials. Similarly, now next I will attach the, already it is 50 gram, now in my hand it is again 50 gram. So I will attach it from the upper side. Okay, now how much it become? It becomes 100 gram. Now you can see the bar is again bended towards the earth more, because yes, weight is more. Again we have to do the same. What we have to do? Just remove it, count the oscillations, and at the same time start the stopwatch. Okay, as soon as the 30 oscillations will be completed, you should stop the stopwatch and note down the time required for 30 oscillations. Same here, 1 2 3 4 5 6 7 and so on. Now you can see as you are increasing the weight, the time will be more, time required will be more, and the oscillation amplitude is also more, and yes, that is why we will have more clarity for the measuring of these oscillations or counting of these oscillations. For 50 gram you can see the oscillation amplitude is very small, and that is why we have to measure, we have to count very carefully. But if we are moving towards the higher and higher mass, then the amplitude of the oscillation is also increasing, and easily you can measure 1, 2, 3, 4. You can consider one of the origin. Now I am considering this is the origin. Okay. Okay, 0, 1, 2, 3 likewise. So oscillation we know as like our simple pendulum oscillation, if it is the mean position, then if it goes to the extreme position, or if it is the extreme position. Now simple pendulum initially at the mean position. So if you have to set it into the oscillation, we should take it to some displacement, so that will be the extreme position, and remove that from that position, so it will go to the another extreme position and will come back to the same position. That is what we call one oscillation. So that's what here also we are doing. We are considering one of the reference point. Either you can consider the top or bottom, or at the mean position also you can consider the reference point, but keep in mind that you should count from that reference point only. So likewise we have to measure or count the 30 oscillation. Now again same for, already it was what, 100, and now this is what, this is now 150. So again you can see the oscillation are now more amplitude, they are having more amplitude, and they will be more easy to count, that is right. So this is how we have to do the observation table. We have to fill the observation table, and yes, similarly you can do for the 50, 100, 150, then we have another mass, it is, then it becomes 200, then 250. Likewise you can take the 5 different sets of reading, and from that then we will find the slope and all that we will see in the calculation part, right friends. Now see here observation table. First of all we will keep the observations, how to find the breadth and thickness, that is depth. Okay, so by using this vernier caliper, we have to take the main scale reading, then circular scale reading, moreover here vernier scale reading, and we know the least count of the vernier caliper is 0.01 in centimeter, 0.01. So if we found that in this way, then we will get the breadth in near about 2.93 centimeter, and the thickness is near about 0.514. Since it is what, this particular thickness is measured by the screw gauge, and the breadth is measured by the vernier caliper. So finally here we get breadth as 2.93 and thickness as 0.514 centimeter of our wooden bar. Okay, right, this is what actually the breadth and thickness. Now let us move towards the reading, let us move towards the oscillation part. So as we can see in the first column of our observation table, we have to write the length of the projecting bar. So we know that we are going to keep this constant. So whatever may be the bar we are keeping, or the cantilever which is free to oscillate in the air, its length is 70 centimeter. And now yes, as I told you, this mass we are going to vary. So for the first 50 gram mass, yes, as I have taken the 3 different trials. For first trial I got the time 12 seconds, for the second trial it is 11 seconds, and for third trial it is 10 seconds. Since this is what the major the minor gap between these 3 readings, that is why only I am taking, or we are taking 3 different trials, so that in average the accuracy will be maintained. So if we take the average of these 3 readings, it will be 11 only. And for next 100 gram, if I take the 3 readings, then the time will be for T1 14 second, then 13 second, then 12 second. The average of these 3 will be 13 second. Similarly for 150 gram, 14, 15 and 14. So yes, it is 14.33. And for 200 gram, first trial will be the 16 second, then 16.5 second, then 16 second, and the average will be 16.66. And for the last we will take the 5 readings. So for the last mass, that is 250 gram, it is 16.75, 17.5 and 17.6, and its average is going to be 17.28, right. Now we know that if we take the average, then this is only the time required for 30 seconds, right? Here we have written 20, but actually it is 30 seconds, right? And to get the time period, that means capital T, we should divide it by 30. Yes, that is what we have done here. To this mean value corresponding to the 50 gram, after dividing 30 we got 0.3666. then for this 13 again it is 0.433, then for this 0.477, and yes, for this 16.66 it is 0.5386, and lastly it is 0.57. now you can see the trend. Since the mass is increases, as the mass is increases, the time period is also going to be increase. Yes, because we know that as mass is attached more, then what we can say, the amplitude of the particular oscillation will also be increased, and it requires more time. That's why the time period is increasing. And yes, this is what the time period square. So yes, just square of these particular corresponding things, and again here also we can see the trend is what, only increasing. As mass increases, this t square is also increases, we know that, and we know therefore the graph between them. So here we have plotted the graph between them. So graph on the x axis we have, right, on the x axis we plotted t square on the x axis, and m, that is mass, on the y axis, right? And yes, we got this curve and its slope is here, and if I found the slope of this, it is m2 minus m1 divided by t2 square minus t1 square, right? I hope you can see this. And finally what we got is the slope is 5000 divided by 5, and it is 1000. what we got is slope, and it is nothing but what, m1 minus m2 divided by t1 square minus t2 square, that is nothing but slope, right? So finally in the formula we have to substitute the value of this slope, or that bracket is nothing but, or whatever maybe, it is 1000. This is what one of the value for B, breadth. This is another value, that is for depth. Length we know 30 centimeter, and remaining values already we know that, right? So let us see how to do that, right? So simply after substituting the values, here you can see 16 pi square L cube divided by BD cube, and this bracket, now this is nothing but the slope 1000, directly we can substitute here. Yes, that's what I have done, 1000. Then 16 and pi 3.14, it's a square, L cube, that means 70 cube, and in the denominator value of B is 2.93 centimeter, D is 0.514, and it's a cube. So after calculating this, finally we can get this 6.308 into 10 raised to 11 dyne per centimeter square, and finally we have to write that as a result. So the Young's modulus of the material of given bar is, we got it is 6.308 into 10 raised to 11 dyne per centimeter square. So yes, this is how the methodology and the calculation part of this particular experiment, which is Young's modulus by cantilever, right? Or we can say Y by cantilever, or Y by bending also. See, so it is an, or we can say it is an oscillating method, oscillation method. So this is all about this particular experiment. I hope you got it, and if you have any doubt, then you can post in the comment box, or if you like this, then hit the like button of our video and share with your friends, and yes, subscribe to our channel so that you will get all the videos of this kind on my channel, and press the bell icon. You will get the notification of our next practical video. Thank you friends, thank you so much.